Hello everyone, my name is Avkash, and in this deep learning workshop part 2, we are going to cover three main things. First, we will learn how to create just a basic neural network using PyTorch. In this basic neural network creation, we will learn how to define the layers and how to create the forward function. That's it. In the second step, we are going to build the same neural network based on our input data requirement. It means we have to manage how the input features has to be processed through layers and the hidden layers, and also make sure that we manage input features and the output classes in our neural network. And we also need to create the forward method so that we can process the input data correctly. In the last part of this workshop, we are going to combine the input data requirement as well as the network architecture with layers and the forward function. So combining these two, we will apply two different examples of heart disease data set as a structured data problem, and we are going to use the MNIST digit recognition data set as the unstructured data input. And using these two examples, we are going to learn how to create just a basic neural network. During this workshop, you are going to learn few very important things. First, how to develop your layers architecture to meet your input data need, and how to create your forward function so that the way you are defining your layers, they can be processed correctly. Our objective is to learn how to add various hidden layers with the input and output neurons in each layers so that we can build our layers for the network, and we can also create the best suitable forward method. By end of this workshop 2, I am sure you are going to build your own neural network for other problems such as fashion data set, such as Titanic data set, supermarket, as well as the loan data set as your homework. So let's get ourselves started. Before we jump to part 2 of this workshop, I would like to recap what we have covered in part 1, all things tensor. If you already have covered that workshop, please jump to the next chapter. In the part 1, all things tensors, we learn about 40 plus different methods that can be applied on tensors. It is very important for us to know the math behind the tensors and how they can be applicable to our deep learning projects. It would be best for you if you spend 5 minutes and run the Jupyter notebook, which is available in workshop 1. So all these tensor specific mathematics or functionality will be fresh for you so that you can be ready for this workshop number 2. So the following our agenda in this tutorial, we are going to cover three main things. Creating the first network model or the neural network using PyTorch. Then we need to understand that how to make our network model work together with our input data, because input data is what processed through the network model. So we need to learn how to manage the input data features so that we could set up our neural network model correctly. And finally, we need to understand that how to define our model and the forward function so that data can propagate. With the PyTorch, we are going to use the neural network.Module. So this module is the base class for all neural network modules, and your model must belong to this subclass of this class. It means if you look into the documentation, the nn.Module is your main module, which you're gonna be using part of nn container, and you see that module is your main one, and your model must be subclass to this nn.Module. So we are going to import torch, and we are also going to import torch.nn and we are going to refer it as nn. So most of the places where we are going to refer nn, you can also refer that torch.nn. And at very first step, we are going to create our very first network model, which is some class of nn.Module. That's important. And we have to define two main functions. First is the init part, which has all the layer definition of your network model. So all the layers you are going to define, including input and output, has to be defined here. And the forward method is the where your data flow from one layer to next layer. It means from input all the way to output, and in between you have multiples of hidden layer. So X will be your input and X will be your output, but that is the processed output. So we have created class. You choose the name and then you subclass based on nn.Module. You are defining the init, and this is a super init, just empty function. There is no layers we have. And then we are defining the forward self, passing the X and returning the X, which is the processed one. Let me create this class. Now we are going to instantiate the model or creating the object from your class. We have got the class, which is the model, and we are printing the model, which is my first neural network model, because that's what defined. Very basic, no consideration of input data, layer, anything. So this is the skeleton of any class. More functions will be added as needed, but this is the very basic function you have to start with. Now, remember that we are creating these new neural networks because we want to process the data. It means the architecture of this model is defined by two main things. The input data, how data is laid out, which is going to be passed through this network, and next step is the network architecture. It means the number of layers. Once you define the layer, then it comes about how the other component within those layers and everything comes next. So we are going to define the tensor data based on my previous tutorial where I talk about all about tensors. Everything we talk about tensors. Here in this example, we will use a transactional data, more structured data. So we have total 100 records. So 100 records of 5 columns or dimension. So these columns are age, income, zip code, this person has house or not, and is married. And the outcome of, we are just trying to find out if this person is going to purchase house or not. So true or false. And so that is our outcome, or the y hat, or the output column. So our input data is going to have these, and our output data will going to have true or false. In the training data, we will have all ones, combination of ones and zero for each record. So if we try to create a tensor for our input data, that is going to look like that. It means we have 100 records of 5 input fields. That is how our data is going to look like. So we have these 5 fields and these are the 100 fields. So for example, if I have 10, it's easier to manage. So for example, if we say we have 10 records, then we can see very clearly these are the 10 records on each field. And I'm using the random, so normalized distributed random data. That's what I am getting here. At this point, once we have defined our input data, now we can use our model object, which is our model object here, and we can pass our tensor to it. So we are passing, and this is NNM, which is neural network model. Now we are trying to print the model T, and as you see, that data was fed into here, and here is the NNM, which is exactly the same. The size is the tensor size, and the shape will tell that this particular NNM is designed, neural network model is designed to process the 10 records of 5 featured data. That's what it is. And if you look into our internals of our network, they are empty. It does not even matter what you are passing. It means there are 3 things we have right now. First, until now, we have no relationship between the tensor and the model created, because the model we have created has no dependency on the tensor, correct? Our model definition is empty. There is no concept of layers. and there's no way to process data. So we have to complete our network in a way that we need to make sure we can manage the input data, then we can add hidden layers as needed, and then we can also forward method. It means the data will be processed. So now let's connect our model and the input data together, where our input data is in the size of tensor or in the format of tensor. So conceptually, we are going to use the pre-discussed example. We have 10 records of 5 dimensions, and we are using 10 records because it's easier to visualize. But once you get conceptually understanding, these 10 records will be tens of thousands of millions, and the dimensions could be 5 to 500 to 5000. And your output classes, currently we are using 2, true 1, and the false 0, but later in other examples these output classes could be 10, 20, 100, 1000 depending on your objective. Layers, in our example, we are going to experiment. We will build some predefined networks, then we will start experimenting to various combinations of hidden layers. So very first we need to look into the basic network with input and output layer with there is no hidden layer. So the definition of that layer we have to define. So we will use the linear, the neural network dot linear. So if we look into the linear layer definition in the PyTorch, as you see that a linear transformation to the incoming data, and that's the formula for that. We need to pass the input features, we also need to pass the output features, and then we need to add the bias, weights, etc. In this workshop today, we are not going to cover anything besides input and output features. So we input dimensions, input features, output classes, output features. Reason I put here dimension in classes, so at least you have a better idea what we are talking about. For example, if you say that you have 10,000 images of dogs and cat, and you would want to classify dogs and cats. So your dimension, your images, number of images, and their dimension will be your input features, and the output classes will be whatever you would want to identify from that. So let's take a very simple single linear layer network where input is 5 and output is 2. It means our input data is 5 and output is 2, and in the forward where the data is going to process, we are just using a very simple forward method, no calculation whatsoever, very basic. Let's define this. Now after the definition, let me visualize this network for you. What we have defined is exactly here. Our input features are age, income, zip code, has house, is married. Output features, if this person is going to purchase house, true, or purchase house, false. Very simple network. This is exactly what we have defined here. And based on that, now we are going to process our input data. So I will go a little more deep down because I have various examples of networks there. Here is our data. We have defined the random 10 records of 5 features data. That's the data, and everything is float, because if you look into here, module support float. So it means we have to pass the float data to our linear layer. We make sure that we have done. We are defining this neural network, passing the T, and you could see the torch size is 10 of 2. Remember, we have learned earlier. This is our model which we have defined, very simple model, and this is the network visualization of our neural network. And whenever we are going to get the result of our layer, we will always get the number of the samples you are feeding in the output. For that reason, this statement print x.shape, when you are passing the data here, you are getting 10 samples of two output dimension. And in this network, what you are actually trying to do is that you are sending the 10 records, and based on your input random data, you are getting the two values. And it's random data, but you can get a conceptually idea how to pass the input data to your network and how you are going to add the layer. So here we have seen a very basic no hidden layer network. Now we are going to introduce hidden layers in our network. And as soon as we are bringing hidden layers, the number of layers and the number of neurons is start popping up for us. So let me define here and then I will explain. So if you look into most of the class definition for our neural network is quite similar. Definition is a class inherited main master class from the nn.Module and defining in it all the layers and defining forward how the math going to work. Here we are adding single layer which is going to process the 10 neurons. It means the 5 features going to be transformed into the 10 neurons. 10 neurons will be transformed into the 2 output classes. And linear 1, linear 2. Again, I'm not using any math. Math coming a little later. But it's just that currently focus is on creating the layers first. Now let's take a look at this visualization of this network. Here is the visualization for our second neural network. First linear layer, input 5 features, generate 10 neurons. Those 10 neurons finally generate your 2 classes as output. So it's a single hidden layer network. And let me define it and let's use the data. Now we are going to pass the data to our model. And the first layer, total 10 records, 10 output. Second layer, total 10 records, 2 output. And if at this point, if we make mistake of not matching this, if we are saying first layer input 5 and 15 of them, and if we are not matching here, let's define it, and if we pass this data, it will say that 10 of 15 is not going to be multiplied by 10 of 2. And that's where the first glimpse of matrix multiplication you are seeing. It means we always have to match sure. If we would want to have a 15, then input for second layer must be 15. If we match this way, just for example, if we pass our data, that is going to work. And the answer is that the input 10 records, 15 output, 10 records, 2 output. So what we have done here, rather than 10 input neurons for this hidden layer, we have decided we are going to use the 15 neurons in that layer. And that's all we make change. And once we made that change, we made sure that the second layer has the same number of neurons to be used as the input. So output will be desired, whatever we are looking for. Now let's add one more hidden layer. I'm going to put this back to 10 so it matches with our image. I will be defining another neural network, 3 layers, input it 5 features, target is first hidden layer of 100 neuron. Second hidden layer is going to accept the 100 neurons coming out from previous layer and converting them to 10 neurons. And the third layer or output layer taking the 10 input neurons and generating your 2 output classes, final output. This is our neural networks and all the layers are defined simply here. Let's define our neural network. Let's visualize it. Depending on what we have defined in our neural network, 5 input fields, age, income, zip code, has house, is married, are here, and 100 neurons are in our hidden layer 1. The output of these 100 neurons is going to go in the layer number 2, which is generating the 10 neurons, and then the 10 neurons input for the next output final layer, generating the 2 classes. After we have defined this, let's make sure it's defined. Let's pass the tensor. All 3 layers is total number of 10 records, but 100, 10, 2. And as you could see here, first layer 100, second layer 10 output, third layer 2. And that's what you are seeing after the processing happened in the forward function, because these outputs are coming from the forward here. We can say here in this x, we are adding x plus x, and here we are adding x plus x plus x. And remember, when we are doing addition of these tensors, because these are x is basically the tensors, the dimensions are not changing as of now with these basic arithmetic. If I define this as it is, and I will pass the data again, math has changed. The internal values of x must have been changed, but the output is still consistent, 100, 10, 10. If we look into the data, you see that you are going to see the 10 inputs for the 10 records and 2 output. If you change your tensor value from random to ones, now all values are ones, you pass that ones data to your network. If you see the result, you are going to see uniform result, because the all ones are there. For that reason, your result is exactly the same for both classes. If you will pass the zeros, all values are zeros. Now if you passing the data, looking into the n, this result. So you should have a very good idea at this point that whenever you are going to define your network, the number of layers, number of neurons in your hidden layer, are they matched correctly? As soon as you make a mistake here, for example, your output is here is 1000, your input is here is 100, you made a mistake, your neural network is going to give you error. Let me define one more neural network. Here where input is 5, output means the next hidden layer has the 1000 neuron, then next one has the 100, next one has the 10, and finally we have the 2. Let's define this network and visualize it. We could understand this network definition with this corresponding image. Input 5 features, next we have 1000, so 5 input returning to the 1000 neurons in the hidden layer number 1. 1000 input goes to hidden layer number 2, coming out as 100 neurons. Hidden layer number 3 taking the 100 neurons and coming out as a 10 neurons, and finally the transformation happened whatever needed, and your 2 output classes are defined. Let's define this, and now we are sending the data, all the zeros, passing the data, t, 1000, 100, 10, 2. As you see here, you are sending the 10 records, 1000 output, 10 records, 100 output, then 10 records, 10 output, and finally your 2 classes. After these 3 different variations of network we defined, now you should have a very good understanding of how you are going to define the layers for your network. Now we are going to focus more on the forward function, where how these network layers data is going to be processed in these layers. And for that reason, I have this template network code, and we are just going to experiment various things here. We should not have that. So at this point, as you see that I have these 5 layers, and based on those 5 layers, we have this forward function, 5 in features, 10 output, 10 to 100, 100 to 1000, 1000 back to 10, and then 10 to 2. Let's define this and pass the data, 10 to 100 to 100 to 1000 to 10 to 2. So your neural network is getting much more diverse because you are adding so many layers. If you make any mistake, so for example, if I make the 100 to 100 here and we do not change here, we definitely going to get an error whenever we are going to pass the data that this is incompatible. The layers transformation, when the data is going to pass between these two layers, the incompatibility going to happen. However, if you look into here, that incompatibility is in this layer. If you do not use the layer 4, this 100 is actually, and then you change this to 100 here, for example, now it will work because you are not using the layer 4, you are layer 3, and then after that you are jumping to layer 5. Layer 4 is no longer existed, and even if you define this layer 4, but if you are not using the layer 4 at all, this connection is directly connecting to this layer 4 defined but not used. Let me make sure I define it. Let me pass the data. It worked. So what you have learned is that it's not what you are defining in your layers, it is what your forward function work. Here we have intentionally defined this wrong layer. But because that layer is not really used in forward function, so impact of that mistake has not been visible. So what you are defining and what you are processing, they both are equally important. Now, various linear operations can be done as long as your matrix math is working correctly. You can do addition, you can do multiplication, various complex mathematics functions can be applied here. And when you are building the real neural network, you are also going to use various computations such as activation or other things. And I will give you a very quick example of this CNN explainer. Here, the input are these, and as you see here, this is the layer 1 where the input was 64 by 64, and that is become the 62 by 62. So what happens is that convolution happens here, then activation happens here. Here, as you see, that convolution happened from this layer to this layer, and this is a fully connected. So if you look into here, all the wiring from every neurons, everything is connected. Activation is happening here, then pooling is happening here, and then after the combination of this is actually going into the next layer. So layer 1, layer 2, layer 3, layer 4. You can get an idea that what we are learning is very basic, but it is very important because the layers is where the inputs are happening. This is going to happen at this layer. Whatever the mathematics happen here, that will be output for this. Because the input here is 60-60, the input here is 22-22, and we will learn that in subsequently as we go further. At this point, if you say that your x is actually the plus of linear 1, if you define, if you pass the data, now there is a problem. Because what we are saying is that the linear 1 is actually input is 5. And so we are adding the x in the linear 2 as here is a 10 of 100, but we are adding 5 plus 10 because that's what we are trying to say. 10 of 10, 5 of 10. It is not going to work. So math has to be adjusted properly. Same thing in linear 3 here. If you see 100 to 100, at this point 100 line linear 3, we can actually do at this point because the x itself is the linear 2 here. So if we want to say this, we can also say x. So it's a linear 3 of linear 2 plus total linear 2. Let's define. And it's going to work. And reason it's going to work because they both are 100, 100. They are matching at this point. So here, this x is self.linear 2. The input is 10 and output is 100. So this X has the input is 10 and output is 100. For this linear 3, the input is 100, output is 100. So if we try to use this math, we try to input our data, that calculation is going to work correctly at X, because X is the linear 2 of X. At this point, if you say self.linear2 of X, that is not, because the X is already the linear 2 now. So it will not be able to work correctly. You can store that variable and then you can use that, might be able to work for you. So for example, if you will say here x1 and you use x1 here at this point, x1 of here, and at this point if you use x1, it is still going to work for you. You see, it still is going to work for you, because once you use X, because X is keep changing as we are moving from one layer to next layer. But here we are taking the input X, is storing temporary in X1, then X1 is passed, last is all X, but here we are taking this temporary X1. So this X, these two additions are still legal. So until now, we are not using this linear layer 4. Linear layer 4 has the input 1000 and output 10. That's where it is. So if you would want to use the linear layer 4, for example here, and we do not do this right now, so it takes the X coming out from linear 3 here, and then we need to make sure that output of linear 3 is, let's make this 100. So linear 4, 100 to 10, 10 to 100. If we pass the data, the 10 to 10 and 100 to 10. Oh, we made a mistake here. So we need to make 100 to 100, because the 10 by 10, 100 to 2. So we have to fix that here. So let's make this 100, 100. Now it should be okay. Now it's okay. So this, yeah. So there are two options here. Either you can make this 10 to 10, pass the data, that's 10 to 10, or you could make it 100 to 100. So those were two options you had in order to make sure your network is defined correctly. Whenever you are going to define your model size, you are going to get the total number of records and the total number of output classes from that layer. So whenever you are going to say your n.Shape, your model, your input data, and the output classes. So for example, if you select the MNIST data where you have 60,000 input images and your output is 10 digits from 0 to 9, your output will be 60,010. Now we are going to look into little more complex forward function. This complex forward function, which is defined, which takes the input data and create the linear, then you see some x plus linear 2, then x2 is self plus linear of x1, and then little more complexity we have added. So here is one example we have where inputs are 5. The next layer is 100 neurons, then next 100 to 5, and let's define this. And here you see that there is no matching. However, the math is going to work. So I'm going to explain this math for you. So let me define this network first. Then let me pass the data. So here is our data we are passing for this, and this is our network shape as each level. 10 records, 100 output in the layer 1. Then next we are again 10 records, 5 neurons, 10 records, 100 neurons, 10 records, 2 output classes. So how it was possible? And as you could see here, there were 3 layers, and at this point we had the 4 different mathematical functions we have used in our forward function. So first x is our 10 records and 5 input features. So we pass that here, and x1 is the linear one. So input was 5, and what your output x1 has become 100 neurons at this point. So at this point we should make sure that is a 100 output. Next, we are taking the x, which is still 5 of 100, then plus linear 2, which is 100 of 5, 100 input, 5 output, that is what, and so that's the linear 2, and we are passing the x1, which is 5 of 100. So linear 2, 500 plus 500, which gives you x2, that is 5 of 100. That x2 is still okay, because at this point, if you do this way and you say return x2, that is actually you are taking x2, just run it, passing, and that is still working because we have stopped that way. Now I will come back, enable these, and bring the x return. In the next layer, we are still using the linear 1, because remember our output was 500, because the linear first layer is still using the 5 features, 100. So we are just passing as it is, because that was our network layer output is. That x2.shape is going to give exact same record for us. This one and this one, that's x2. Now taking the x2 and passing to the x3, where input is 100, output is 2. Input is 100, output is 2. And after this calculation, you are going to get your network like this. So please do experiment again and again, so you could understand how important it is for you to create your forward function correctly. Now I will be using a real world problem and try to create a very basic network and feed that actual data, so that we know that our neural network is correctly designed. Let's look into this data set, very popular heart disease data set. It has 303 rows, 75 features, but 75 features are not mostly used, as these 14 features are very popular. 0 to 13, these features are various metrics, data related with heart disease conditions report. The last, this is the predicted value, predicted attribute, whether somebody has heart disease or not, so 0 and 1. So based on this, we have 75 columns, but 14 columns are the most used and applicable. Total 303 records, total input is 14 features. Output has a 2 classes, true or false. So this is your input data. I'm importing pandas and numpy. This heart disease data set I have already stored at one of my public GitHub repo. So I'm loading this data set and I'm creating the input and output target. Input I'm using from 0 to 13 features, and the last one is a target, and the column name is target. Here all the columns up from age all the way to THAL, as we have seen here, from age to THAL are the input features, and the final, this is our input data really look like, and here is our target columns, target, and if you would want to see the value, there will be 0 and 1. As you see, 0 and 1 value in df target. Next step, we are going to convert our input and the target to numpy array. So this became our numpy array. So no big change. This is our data frame. We are converting it to numpy array. If you would want to see the target, it's gonna be again all the zeros and 1, hiding it. After that, we are taking the input array, changing that to float 32. Why we are doing it? Because we have to convert tensor and float 32. So first the data type is converting in NP array float 32. Then we are using the torch from numpy. So from numpy array we are converting them to tensor. So input and targets. Here is your input and here is your target values. So now we have tensors available. So our input tensors available. At that point, you could see that our inputs are 13 field, target is 1 field, both input and targets, they are 303 records. So now we have to create the heart disease neural network model. So this is our heart disease neural network model, main class. So we are subclassing ourselves. Our input 13 feature, this is just the hidden layer, 100, next hidden layer, 10 and from 10 to 2. We have already looked this earlier. So in this example, the only difference here is that these 5 columns which we have used earlier as an example are the 13 columns input here. Next, first hidden layer has the 100 neurons, second has the 10, and final output is 2, yes or no, heart disease yes, heart disease no. Let's define the network. Defining the model, so it's a H model, heart disease model. And now what I am doing is that I'm taking the 303 records and 13 feature and creating the random tensor. Reason I'm doing is that because we cannot pass this data directly to our PyTorch network. You need to use the data loader and other capabilities. That is the next tutorial just after this. So the tutorial number 3 is going to cover data sets and the data loader. How to load data within the neural network in PyTorch. So I don't want to bring the data loader, all that complexity. So I am just creating a very simple random 303 records of 13 feature random tensor that's defined here, and I'm passing that tensor to our heart disease model. This is our heart disease model. Thus you see input 303, 100 neurons, 10 neurons and 2, all 3 layers that we have defined here. If you would want to take this and you want to define the shape of your model, hm.shape, hm.shape. Do you know what the answer should be? Take a pause. Your answer should be the total number of records you are passing and the output classes. 303 records and 2 output classes. Now if we take the MNIST problem, where we have 60,000 input examples and 10,000 the test set. So 60,000 record of each record is a size of 28 by 28 image. So when we take the image features are the total number of pixels in giving image. So you take 28 height and you take 28 width and you multiply them, so you can get all the pixels in a straight line. So that will be your input feature. So your input will be 60,000 records of 784 features. Your output will be 0 to 9 digits. And thus the output you would want in 10 different classes. So if you pass this input data, your neural network will take input features, your output are the 10 features. This is your network, MNIST. We are creating the random 28 by 28 records. We are passing that tensor to our MNIST model. Here is our MNIST model. If you would want to get the shape of MNIST model, mn.shape, 60,000 record of the 10 classes. If you would want to add one more layer, where the 10 neurons are used for 10 output classes, you can add that one too. Define your network again. Make sure MNIST model is object, has the latest network. Data we don't need to create, we already have that. We can pass that data. Now you are going to get one more step, 10, and shape will still be 60,000 record of 10 classes. These 2 examples we have used today. Tomorrow we are going to use the actual data using the data loader for the heart disease problem as well as the MNIST problem, and we will build the real network, and then we will do the real classification of very basic network. After we have taken the 2 real world example and they build very basic but correct neural networks for our need, next step comes the nn.Parameters. If you look into the containers, very first is your parameters. So parameters, kind of tensor that is to be considered a module parameter. So I'm using this article because those examples were very easy for me to explain. So parameters are the tensor subclass. Whenever you take the parameters, because you are defining a neural network and neural networks has these parameters, so you can extend those parameters with the help of nn.Parameters class. And it is the subclass of the tensor class. So let's look this example and then follow what the nn.Parameters gives us. So first I will be defining a custom neural network. Here you see that the linear layer is a custom layer. Input is 784 features. Outputs are the 10 features. It means this custom linear layer is going to have a lot more definitions built into inside here. And then our output is just the very simple forward function here. So first we need to define this. Here we are taking the insides and outsides. So insides is 784 features, outsides are 10 classes. Then using the nn parameter, we are just generating the random normalized data based on this size and based on this output size. Then we are also adding the biases, which is based on output size. So let's define this first. And here you see that x forward method is a matrix multiplication of the self.weight and the self.bias. So whatever the weights are and whatever the biases are, we just want to multiply them. So that's our custom linear layer, and that's our network. Now we are passing the random 100 record of 784 features, that is our x. Then in the custom neural net, which is there, we are defining first. So let me define this first. Now let's print the model, your custom network. Let's use the model of x, because at this point we haven't passed the data to us. So now we have passed the data, which is 100 records of 784 features. equals model x. Now dot size here, and finally dot shape. 100 records of 10 classes. So you can get an idea that what we have done here, we have created a custom parameter, and just using the nn parameters, we have created these weights and biases for our neural network. Here we could actually print them. We can say print. Let's define custom linear layer. Our network is defined. We have to define our model again correctly. So model is custom linear layer, passing the data x. Now you see the weight shape is a torch of size 784 input, 10 output. So if you would want to print the weight, we can just print the weight also. So you can get an idea that whatever was input, whatever our output size, that's how we have created the weights and biases, and then we are just multiplying weights and biases. And because the 10 is valid, so matrix multiplication is going to valid. If we change here output size plus 1, for example, now it became 11. Let's define this. And if we are going to pass this x, it will not work, because 11 will not going to multiply by 10. Look at this, correct, define, passing the data, everything is okay. As an homework for you, please try to create your own neural network for the Titanic data set, which you can get from here, and you can also look into Kaggle for the supermarket data set for market basket analysis, as well as the loan data set. And try to learn by yourself by creating these neural networks for you. So before we conclude this workshop, let's take this Jupyter notebook and save it to GitHub, and it is going to be available in this PyTorch tutorials folder at this DeepWorks public repo. And now this Jupyter notebook is available for everyone to try. Let's spend a few seconds to recap what we have covered in this workshop number 2. We started this workshop by creating a very basic network model with the layer definition method as well as the forward method. Then we learned how we need to create the layers and hidden layers to manage the input data requirement, combining the features as well as the output class. Then we use a couple of different structured as well as the unstructured data examples, and we build our models. We covered some of the complex forward methods as well as the simple as simple, to make sure we understand the requirement of the hidden layers, input and output neurons in those layers to match our input data feature, as well as to make sure we can manage the output data or output feature classes. Overall, the objective from this workshop was for you to understand how you can create your own neural network for whatever input data requirement you have. We are creating the very simple linear network in this workshop. However, this is the start. As we progress further, we are going to create even more complex networks. So the next workshop number 3 is going to cover the data specific content. It means we will learn how to use the PyTorch dataset and the data loader functionality, so we can load the existing data set which are available in the PyTorch, as well as we can just load any of the structured or the unstructured data set. In the workshop number 3, we are going to use the heart disease data set as well as the Titanic data set as the structured data input problem, and we are also going to use the MNIST as well as the fashion data set as the unstructured data, and we are going to build our own neural network to solve the problem as defined in those publicly available data sets. And if you look into the in front of you, the PyTorch supports a wide variety of neural network architecture. It means there is a lot to learn for us. Some of the concepts such as linear, we have learned today, linear, nn linear and the nn parameters. However, there is a massive amount of other architectures we need to cover. So we have just started our learning, and as we progress, we are going to cover even more of these architecture in one individual workshop, so that we can learn as much as about those architecture and we can include them in our neural network. So that's all I have for you in this workshop number 2, deep learning workshop. I hope you have enjoyed the content. I do appreciate your time, and I am going to look forward to see you in my next video. Until then, thank you so much for your time.